Section 15.4. Using the postulates to understand the particle in the box and vice versa. Quantum mechanical postulate 1. The state of a quantum mechanical system is completely specified by a wave function psi of the positions of the particles. If you know psi, you know everything about the system. The wave function must be single-valued, continuous, and finite. Now let's look at this example. This is the wave function of one-dimensional particle in the box. And this function is single-valued, it's continuous, and it's finite. Now postulate 2. For every observable in classical mechanics, there exists a corresponding operator in quantum mechanics. For example, we have this momentum operator, we have this kinetic energy operator, and you can apply these two operators to this wave function of the one-dimensional particle in the box. Or you can try this for 2 dimensions, 3 dimensions as well. Each dimension is independent of each other. Now postulate 3. A psi is equal to A psi. This is a operator A, uppercase A, and this A is lowercase a. This lowercase a is the eigenvalue of the wave function psi. So now let's try a few examples. Let's measure the kinetic energy of this particle in the box. We don't really have to do any experiments. When I say measure its kinetic energy, I mean applying the kinetic energy operator to its wave function. That's it. So the kinetic energy operator is this. We apply this kinetic energy operator to this. What's the result? The result is going to be n squared h squared over 8ma squared. That's it. How do we get the momentum of this system? Well, it's simple. We just apply the momentum operator to the function. This is the momentum operator. We apply this momentum operator to this wave function. What's the result? Well, unfortunately, in this case, the result is a cosine function. That means this sine function is not an eigenfunction of the momentum operator. That means there's no way to know the exact value of the momentum of the particle in the box. Right? So this is very important. Earlier we learned the magnitude of the momentum can be determined exactly. However, we cannot determine the momentum vector because we do not know the direction of the movement of the particle. This particle may be moving forward and backward at the same time. So that's why we say there's no way to figure out the value of the momentum. All right? The directional momentum, to be exact. We do know its magnitude, but we do not know its direction. So again, if I give you 2 data points, 1 and -1, I tell you x is equal to 1 and -1 at the same time. I tell you 60% chance it's 1, 40% chance it's -1. Well, and then if I ask you, do you know the exact value of x? You should say no. Postulate 4. If a system is in a state described by a wave function psi, then the average value of the observable corresponding to this operator is given by this equation. You need to evaluate 2 integrals. On the bottom, it's just the integral of the squared modulus of psi. Again, the squared modulus of psi is simply the complex conjugate of psi times psi. Okay, over here on top, it's going to be a little different. You need to replace this psi with a psi. A psi is to apply the operator A to the wave function. All right, you need to do this operation first and then do multiplication. Now, if psi is normalized, that means the bottom integral is 1, and then we have a simple expression for the value of, for the expectation value of A. All right. This notation is the expectation value of A, or the weighted average of A, or the probability weighted average of A. Well, now we can actually calculate the weighted average of the position of the particle in the box. Let's look at the one-dimensional particle. This is the expectation value, or the average value, or the weighted average value, or the probability weighted average value. All right, and we know this wave function is normalized. So we have this wave function here, and then we apply this x operator to psi. And if you apply the x operator to a function, it's just the multiplication here, x times that wave function. So you need to integrate this function. I know it's complicated, but without doing anything, we understand the wave function is symmetrical on the left of 1/2 of A versus on the right side of 1/2 of A. Alright, so without doing any calculation, we guess the average value is going to be just 1/2 of A. Also, you can actually honestly evaluate this integral, but in the end, you will get 1/2 of A. Alright? This is not trivial to evaluate this integral. I think you need to do a lot of variable substitutions. So first, you need to change this to 1 minus cosine 2 theta over 2. And theta is just n pi x over A. That's your theta. You need to do some variables substitution. And then you need to somehow move that cosine theta in here to convert it to d sine theta. And then starting from there, you can gradually simplify this integral. But in the end, I guarantee you will get 1/2 of A. Just by looking at this wave function, it's 1/2 of A. It's symmetrical with respect to x equals 1/2 of A. Alright, postulate 5 is the time-dependent Schrodinger equation. So this equation is postulate 5. Basically, it tells you how the wave function changes with time. And this function governs the entire universe and anything inside the universe. So we can propose a time-dependent solution for the time-dependent Schrodinger equation for the particle in the box. It's going to be a linear combination of two different states. Over here, we have sine n pi x over A. Over here, we have sine L pi x over A. It looks strange. You may ask, what's the quantum number of the particle? It's both n and L. It's both n and L. All right? And we'll put a coefficient here and another coefficient here. All right? So the probability of finding the particle with a quantum number n is Cn squared. The probability of finding the particle in level L is Cl squared. Also, we need a function of time here and here. Look at this function. It's the sum of two products, the product of a function of x and t. And over here, it's also the product of a function of x and another function of t. There's no way to separate this into the product, a single product of a function of x and a function of t. Look, it's the sum of sine function of x and exponential function of t. And over here, also a product of sine function of x and exponential function of t. There's no way to further simplify this. All right? Again, you will be able, if you measure the energy of the particle, you will be able to get two different values. One is n squared h squared over 8ma squared. The other is L squared h squared over 8ma squared. All right? The outcome is probabilistic. The probability ratio is here. All right? Now we're going to verify this equation. We're going to plug in this equation. This is a very complicated equation. This is the time-dependent wave function for the particle. I'll plug in to the left-hand side. I'll plug this equation to the right-hand side. And I will prove this equation holds true. So the left-hand side is each side. So I'm going to apply this kinetic energy operator to psi because the potential energy is 0. Alright, so when I do that, I apply the kinetic energy to the left-hand side and right-hand side separately. Left-hand side, right-hand side separately. This is the eigenvalue for this function, and this is the eigenvalue for this function. Two different eigenvalues. Again, because n is different from L, we cannot combine these two. Now let's look at a simplified expression for this. Okay, this is just E sub n, right? So E sub n here, and this is just E sub L, the energy of level L. So this is the simplified form. Now let's apply this IH bar delta over delta T to psi, okay? And then the result is this. So basically we need to take the first derivative of psi with respect to time. The first derivative of this guy with respect to psi, you will get with respect to time. The first derivative of psi with respect to time. So that means the first derivative of this exponential function should be itself multiplied by negative I times En over h bar. Okay? Negative I E sub n over h bar. Alright? So if you do that, and then you multiply this negative I En over h bar by IH bar. H bar and h bar cancel. I times negative I is 1. I think you will just get E sub n, the energy of level n, multiplied by this term. Over here, you will get E sub L times this term. Alright, so again, you get E sub n times the first term in the wave function, and E sub L times the second term in the original wave function. Now you compare this term, this expression, with this expression. They are exactly same. So this time-dependent Schrodinger equation holds true. And again, we have two possible outcomes. If we try to measure the energy of the particle, it can be this or this. Finally, postulate 6. It's not related to the particle in the box problem, but we can put electrons in the box. We can put helium atoms in the box. They are different. Electrons are fermions. Helium atoms are bosons. I'm talking about helium-4. Helium-3 is also a fermion, but let's just talk about the helium-4. All right, let's look at these two cases. Fermions have a half integer spin number. So, for example, electron has 1/2 spin number, and carbon-13, hydrogen-1, nuclei are also fermions. Look at this spin number of the hydrogen-1 nucleus and also carbon-13 nucleus. And also phosphorus-31 is a fermion. What about bosons? Bosons have integer spin numbers, such as hydrogen-2 is a boson, nitrogen-14 is a boson. So now helium-3 is a fermion, helium-4 is a boson. So what's the difference here? Fermions, well, we learned this. Fermions, such as electrons, cannot have the same set of quantum numbers. That's a violation of postulate 6. Bosons have a different rule. The wave functions for bosons should be totally symmetric. Alright, so let's not worry about the bosons in quantum chemistry. Let's focus on the fermions. For fermions, their wave functions must be anti-symmetric. That means if you swap two fermions, the sign of the wave function must change. And that results in this Pauli exclusion principle. Okay? No two electrons can have the same set of quantum numbers. That means when we look at the particle in the box problem, we can generate many energy levels, right? N equals 1, 2, or 3, or 4, or 5, etc. In each energy level, we can accommodate only two electrons, one with alpha spin, one with beta spin. That's it. So that's for fermions, such as electrons. What about bosons? Okay, we can put any number of bosons in any energy level.